Good morning, students. Welcome to your Chapter 6 review video. In this video, I'm just going to go sort of briefly through everything that we've done in Chapter 6 to try to sort of help you inform your studying, figure out what you remember, what you don't remember, what you maybe need to go over again. And yeah, then we'll sort of get prepared for our test. I'll just, like I said, go section by section through sort of what we talked about, the types of problems that we saw, the types of things you may be asked to do on your test. To start off with in Chapter 6, we sort of brought ourselves back to the unit circle, and we started talking about solving trig equations in the first section just from our unit circle. Okay, so we were solving trig equations that look something like this. Maybe the sine of x is equal to 1/2, right? This we can solve for the values of x, the angles that we would put into the sine function that would equal 1/2, right? Angles from the unit circle that have a sine value of 1/2. So, of course, if we go to the unit circle, sine is 1/2 at this point and this point. So this is our old friend pi over 6, and also 5 pi over 6. Right, so those are the two possible answers. Remember, for sine, we draw that horizontal line across to find the other one. And we also talked in this section about restricting the values of x just to the unit circle, right? 0 to 2 pi, or going around and around and around and around again. Remember, if we do go around and around and around again, we just go plus 2 pi n, because that indicates adding one whole time around the unit circle, or if you made n a negative integer, it would be going backwards, taking away. So we do that to both of these. If the domain is unrestricted, we put plus 2 pi n, right? Just so as a clarification or a reminder, when we do take the test on that Google form, we'll just use pi for pi. And it can be helpful if you want, especially when you're putting it here before an n, if you just put it in parentheses. So, if you ever have to type it into something like that, right, that would be 2 pi n. That's what that would indicate to me. Yeah, so solving trig equations from our unit circle just sort of involved, okay, sine of x is equal to this. Where do I find that? Now, we also did something, like this. Like, let's say we have 2 cosine of x plus 1 is equal to 0, right? So now this, we have to do a little bit of work first, right? We have to get the cosine of x alone by subtracting 1 and then dividing by 2. So what we end up with is cosine of x is equal to negative 1/2. And then this is something we can solve from our unit circle, right? Cosine being negative 1/2 would be up here, and down here be 2 pi over 3 and 4 pi over 3. And then we can plus 2 pi n if we need to, right? So remember that we do sometimes have to get the cosine or the sine piece alone first, okay? So that was the first section. The second section, we talked about solving these equations without needing the unit circle, right? Or specifically, we talked about solving equations that we can't solve with the unit circle. Something like 3 times the sine of x minus 4 is equal to negative 2. Right, so this equation, again, we can get the sine by itself, plus 4, right? That makes positive 2, and then we divide by 3 to get rid of that. So the sine of x here is equal to 3. Sorry, excuse me. Sine of x is equal to 2/3. So when the sine of x is equal to 2/3, 2/3 is not a value we have on our unit circle, right? No point on our unit circle has a sine of 2/3. So when we ran into this type of trig equation, we had to use sine inverse. Okay, so remember, if we put sine inverse on our calculator of what we know the sine is equal to, of 2/3, that is going to tell me the value of x, right? So going to the inverse allows us to flip the x and the 2/3, right? Swap those around. So we do this on our calculator, sine inverse of 2/3, and we get a value that is between negative pi over 2 and positive pi over 2, right? If we're thinking in radian mode. Remember that the sine inverse function, we had to restrict the range, right? So that it was a function, because remember the sine inverse function sort of did this across the y-axis back and forth. So we had to cut it off, right? So we cut it off negative pi over 2, positive pi over 2. So it's just the right-hand half of the unit circle, right? It's just this half over here is what our sine inverse can give us. And then we have to do some work to find the other side. So if we do the sine inverse of 2/3, and I do it in radian mode, I get in this case that x is equal to 0.7297, so about 0.73 is what I'm going to say. Okay, 73. Actually, I'm going to do 4 decimal places. That's what I want you to do on the test, at least until your final answer, is do 4 decimal places, 7297. Okay, so that's one angle in radians from my unit circle where the sine is 2/3. Okay, so that would be my quadrant 1 answer. That would be right about here. Yeah, it's right about here, almost exactly halfway. Okay, so that's right here. And then remember, the other one is over here. And when we did the sine inverse, remember that this little angle is the same as this little angle. So we can simply do pi, or 3.14, minus going back up whatever my first answer was, right? So my other answer is that x is equal to pi minus this number, 0.7297, okay? So if I do pi minus that answer, I can do minus, I get about 2.4119. 2.4119. Okay, so that's my other value of x. So for sine, remember, for sine, to find the other answer that the calculator does not give us, we have to do pi minus the answer that we got from the calculator. For cosine, we have 2 options, right? We can either do simply negative version of the answer, okay, just to go the other way, or we can do 2 pi minus the answer if we need our answers to be on the unit circle, okay? So if the problem says anything about, between 0 and 2 pi, for cosine, you're going to have to do 2 pi minus the answer. If it doesn't do that and just wants, 2 answers or whatever, you can just do the negative version. Or if it wants all the answers, you can do the positive version and the negative version plus 2 pi n, round and round and round, okay? If you have questions about that, just go ahead, reach out to me and let me know that. So that was sort of the second section. We talked about inverse sine and cosine, the restricted ranges, right? How cosine is just the top of the unit circle, sine is just the right-hand side. And we used this to solve trig equations that weren't on the unit circle that we have, right? Or that weren't marked exactly on the unit circle. Then we talked also about inverse tangent. Okay, we talked about tangent inverse and how when we remember that the tangent graph originally looks, something like this, where it's got a bunch of these guys, right, all next to each other, all over and over again. And of course, they all do that little whoop thing right at 0, but whatever. When we tip it, then when we inverse it, they turn to, instead of stacking up like this, right, they stack up horizontally, or excuse me, vertically. So we also restricted the range here. But remember that there was no restriction on the domain, okay? Sine and cosine inverse, we weren't allowed to put in anything besides numbers between like -1 and 1. But for tangent, we can put in anything, okay? We can put in literally any number into tangent inverse, and it will give us some angle, okay? And tangent inverse also gives us an angle on the right-hand side of the unit circle, okay? Negative pi over 2 to positive pi over 2. So tangent inverse is also this side of the unit circle. And then in order to find the other answer, remember, we just have to jump across the unit circle. So we just simply have to add pi or subtract pi, I guess would work also. So, this answer from the calculator, when we do tangent inverse, which is on our calculator, we can take the answer and we can add or subtract pi, and that'll give us the other answer on the unit circle, okay? We also talked in this section about the angle of inclination. Remember, we sort of jumped back to linear equations briefly, and we drew ourselves a linear equation, and we talked about the angle that this makes with the x-axis, right? We call the angle of inclination is related to the slope of the line. So what we said was that the tangent of that angle theta, of the angle of inclination, is equal to the slope, is equal to right, change in y over change in x, or slope. So if we do the tangent inverse of the slope, that will give us the angle of inclination. Okay, so we can take the slope and find the angle of inclination using tangent inverse. We can take the angle of inclination and find the slope of the line by using tangent. Okay, and do remember that this was an example where we went back to degrees, potentially, back to degree mode on our calculator. If that's what they give us the angle of inclination as, a number of degrees, say 40 degrees or something like that. But sometimes they'll ask for radian mode. So just be careful about that on your calculator when you get to the test. The next two sections were about all these formulas that allowed us potentially to use what we learned in the first part of this chapter to solve more complicated trig equations. So we talked about angle, sum, and difference formulas. I'm not going to write them all out here because they should be in your notes. But remember, we had a formula for, like the sine and cosine of a plus b, sine of a plus b, cosine of a plus b. And we also had formulas for the minuses, a minus b, and for sine and for cosine. So remember, this allowed us to simplify some things, especially if we saw something like, if we saw, let's say, the sine of 3x times the sine of 2x minus the cosine of 3x times the cosine of 2x. Right, so we could take this and look back at our formulas and think, oh, this is really just the cosine angle sum formula. So this is really just the cosine of 3x plus 2x, which we can then simplify to 5x, and it just makes our life a lot easier, right? So that was sort of the point of those angle sum and difference formulas. The same for the double angle formulas and half angle formulas from the next section, okay? So we had formulas for the sine of 2 times an angle and cosine also. And we had formulas for the sine and cosine of half an angle. Remember, then we went to theta over 2, but it doesn't really matter. You could do a over 2. It doesn't matter what variable you're using. But that angle divided by 2, and we also had formulas for the angle multiplied by 2, okay? Remember cosine double angle formulas? There was actually 3 different versions. Right, they all involved sine and cosine squared minus sine squared, or 1 minus 2 sine squared, or cosine 2 cosine squared minus 1, and so on. So these formulas again should be in your notes, and they not only allow us to solve more complicated trig equations, but we also looked at an example where we have, let's say, we know that the sine of A was equal to 3/4. And that the cosine of B was equal to negative 3/5. Right? This was all the information, and then of course the quadrants for the angles was all we needed to find all of these things, right? Because all of these formulas are based on the sine of A, the cosine of A, the sine of B, the cosine of B, and this information, if we make ourselves a triangle, right, for A, and we know that the sine is 3/4, we can find this value here. 16 minus 9 is 7. This would be the square root of 7, right? So the cosine would be radical 7 over 4. That's cosine of A. Okay, and then we could just find the sine cosine of both of these angles and use our formulas to find all of these other angles as well, okay, or all of the other values, I should say, for sine and cosine. And then in our last section, we talked about solving more complicated trig equations. Okay, so these were the types of equations where we maybe had to simplify some things down, or we even saw something like this, right? We saw sine of x times the cosine of x is equal to, let's say it's equal to radical 3 over 4, right? So this equation can be simplified if the left-hand side were to say, let's say 2 times the sine times the cosine, right? Because remember, 2 times sine times cosine is our double angle formula for sine. So if I multiply this side by 2 and I multiply this side by 2, this side then becomes radical 3 over 2. And the left side I can rearrange based on my formulas, right? So we're using these formulas to simplify these complex equations. And we get, this would be the sine of 2x is equal to radical 3 over 2. And then once we just have the sine of something, we can go to our unit circle, right? We can find the points on the unit circle where the sine is equal to radical 3 over 2. And then we get that whatever was in the parentheses is equal to, in this case, pi over 3 and also 2 pi over 3, right? So we then solve these by dividing by 2, right, which is like multiplying by a half. And you can go back and watch this video if I'm going through this a little bit too quickly. But solving these complex trig equations sometimes involve dividing by 2 after we sort of solved from our unit circle because of these double angle formulas. Or if it's a half angle formula, we might end up multiplying by 2, but that would be a real complicated looking equation. So we end up here with pi over 6, and this one ends up being pi over 3, actually, right? Because 2 times a half becomes 1 pi over 3. So then, of course, if we were on an unrestricted domain, remember that we need to plus the 2 pi n before we divide by 2. So it ends up being plus pi n when we divide away that 2. But like I said, go back and watch this video if you're a little bit unsure about solving these equations. Or if you want to go through another example like this with me, let me know. In this section, we also looked at a zero product property example where we had this trig thing multiplied by this trig thing equals 0, and we could set each of them separately equal to 0 and so on. So if you have any questions about any of these sections or anything that you're unsure about or want to see me do more examples of, or just want some clarification on, please reach out to me. Let me know that soon before you take your test. Otherwise, good luck on the test, and we'll talk to you soon.